So now let us come to the phase plot. So what do you think will happen to the phase? So please note that the phase of this particular factor is going to be minus tan inverse of t omega, right. So what do you think happens to the phase? So if you calculate the phase of omega versus g of j omega, what is going to happen? As omega tends to 0, the phase tends to 0 degrees. When omega is 1 by t, which is the corner frequency, what is the phase? It is going to be minus 45 degrees, right. So you are going to get minus tan inverse of 1, right. So and then like as omega tends to infinity, the phase will tend to minus 90 degrees, okay. So it is a smooth curve, right. So that is what is going to happen. So if you plot the phase plot, this is what is going to happen, okay. So let us say we plot against omega the phase of g of j omega in degrees, what are we going to get, right. So let us do that. So once again I take 1 by capital T, which is a corner frequency. Let us say I take 10 by capital T and 0.1 by capital T. Yes, typically you will see that in most Bode plots, like we essentially plot the Bode plot around the frequency range of interest, right. And by and large, like you choose a frequency range and you go 1 or 2 decades either side. That is typically the range of interest, right. That covers a pretty broad range, okay. So that's why I am taking 1 decade above and 1 decade below a particular frequency, okay. So that's what is happening. So essentially we are going to have 0 degrees, right, and let us say this is my minus 90 degree line, okay, and let us say in between I have minus 45. So all of us know that how the tan inverse plot looks like. So I just need to make sure that like I pass through 1 by t and minus 45, right. That is important. So when I start from low frequencies, like I am going to have values which are very close to 0, then what is going to happen? I am going to have an inflection point at 1 by t and minus 45, then the curve just goes to minus t, right. So that is how the phase curve is going to look like, right, correct, right. So that is the phase plot, right, of this first order factor, okay. Yeah. So what we have done is that like we have plotted both the magnitude plot and the phase plot for the factor of the form 1 by capital Ts plus 1, right, okay. So now the question becomes, like what happens to the reciprocal? Same story, like let us quickly run through what happens through the reciprocal. But before we do that, let us look at this magnitude plot, right. So and on this plot, let me plot the actual one, right. So the actual one is going to be, we are going to have an error of minus 3 at the around like let us say minus 3 decibels at the corner frequency. So the actual plot is going to be something like this, right. I am just drawing an approximate curve just to illustrate the point, okay. So the actual curve is going to be something like a smooth curve like this, okay, which will so the red one is the actual, right. So that is just illustration there, right. So if you look at the magnitude plot of this factor 1 by Ts plus 1, right, what can you immediately say about its characteristic, So does it appear familiar with something which you already learned, So you can observe that it has the characteristics of a low pass filter, right. So because what it does, if you transmit signals, okay, let us say like you consider this 1 by Ts plus 1 as a block, okay, and you provide sinusoidal inputs, right, sin omega t or cos omega t, and then like you ask yourself the question, what am I going to get, right, as the output. So you see that if as long as my frequency is within 1 by capital T, which is the corner frequency, the by and large the magnitude of the input signal is not attenuated, right. So it allows it to pass. Of course there is a phase shift, right, but beyond a frequency for a frequency beyond 1 by capital T, what's going to happen? There is going to be an attenuation, right, and higher the frequency, higher is the roll off. Okay, so what people call as roll off or high frequency roll off typically, okay, this is just a term which one may encounter in frequency domain analysis. Okay, what is called as high frequency roll off is just to indicate, you know, like at what rate is my magnitude curve dropping, okay, at high frequency. For example, here the high frequency roll off is minus 20 decibels per decade. Okay, so for the first order factor that we have plotted, right. So because as frequency keeps on increasing, the essentially the rate at which the curve is going is at minus 20 decibels per decade. That's a slope, right. That's what is called as high frequency roll off. So you see that as frequency increases, you know, like I'm going to have lower and lower magnitude. So what is going to happen if I give a sinusoidal input whose frequency is, let's say 10 by capital T, right, the magnitude is going to be scaled by minus 20 decibels. What is minus 20 decibels in the what to say absolute unit? That's going to be 1/10, right. So the magnitude of the sinusoidal signal with a frequency of 10 by capital T is going to be 1/10 at the output. So you can immediately see that you are having the low pass action, right, low pass filter action. It's attenuating high frequency signals, right. So 1 by T capital T being the cutoff frequency, you know, like as far as the low pass filter is concerned, right. Okay. So you can immediately see that the definition of bandwidth also applies, right. So what is bandwidth? What is cutoff frequency? See, you take any factor, cutoff frequency is a frequency at which the magnitude becomes lower by minus 3 decibels, right, when you compare it with the low frequency constant value. Here the low frequency constant value is 0 decibels. At what value does it becomes 3 decibels lower than the low frequency value? 1 by capital T, right. What is 3 decibels lower than the low frequency value here? Here the low frequency value is 0 decibel, right. What's 3 decibels below 0 decibel? Minus 3 decibel, right. So you see that the transfer function of this form achieves minus 3 decibels at capital 1 by capital T, which is the corner frequency. So in terms of filtering terminology, that's called as a cutoff frequency, right, and the region frequency range between 0 and the cutoff frequency is what is called as the bandwidth. So if you map this term to the transfer function of, let's say, a sensor or an actuator, right, let's say in practice you model a sensor or an actuator using this first order term, which is very common, by the way, in practice. Okay, what's going to happen is that this, if you give me the transfer function, I can immediately tell you the bandwidth. Let's say I give you a transfer function for an actuator, right, as 1 by 0.1 s plus 1. I immediately know that T is equal to 0.1 by comparing with this. So what's going to be 1 by T? 10. So cutoff frequency is going to be 10 radians per second, right. So the bandwidth of that actuator is going to be 10 radians per second, right. So you can immediately talk about bandwidth and cutoff frequencies, right, once you have this structure, right. So I'm just talking from a practical perspective, you know, like, okay, all this mathematics is fine, but from an engineering perspective, you know, like these concepts are commonly used. So please remember, okay, these ideas, right. Okay, fine. Okay, so that's the actual curve. So and that's the phase plot, right. So now what's going to happen when we have a factor of the form Ts plus 1? So we consider 1 by capital Ts plus 1. So let's now consider the reciprocal, right. So Ts plus 1. So T is greater than 0. So immediately we see that G of j omega is going to be Tj omega plus 1. So this implies that the magnitude of g of j omega is going to be 1 plus t square omega square square root. Yeah.
Previous case, that graph, case thing. Normally, with a linear scale, then this is the graph for tan inverse. Isn't it so? The graph. But this is tan inverse graph for the linear scale.
Okay.
But now the scale is.
Why don't you plot and check? Okay, good question. Okay, so please go to MATLAB, plot using a linear scale and logarithmic scale and check. Okay, please check. Okay, so overlap on the same plot, and then like so I will just write homework here just to make sure that you remember. You know, all of us remember. I will also do that. Okay, plot the phase plot using a linear scale and logarithmic scale for omega. Okay, great, fine, please do. You assume some values for capital T and then like okay. So let's come back to the reciprocal. So if g of s is Ts plus 1, g of j omega is Tj omega plus 1, and the magnitude is going to be square root of 1 plus t squared omega squared. So obviously in terms of decibels, it's just going to be 20 log square root of t squared omega squared, right? So what about the phase of g of j omega? It is going to be just tan inverse of t omega. So now you are going to help me with it. So it's pretty straightforward, right, to essentially conclude these things. So what is going to be the low frequency asymptote? Of the magnitude plot, by the way. It's going to be the 0 decibel line, right? Same, as omega is lower than 1 by capital T, it's going to be 0 decibel, right? It's going to tend to 0 decibel. What is the high frequency asymptote? As t omega becomes much larger than 1, it's going to be 20 log of t omega. See, what was minus 20 now became plus 20. Same concept, right? So now when omega is much lower, greater than 1 by capital T, 1 plus t squared omega squared can be approximated as t squared omega squared. Take the square root, you get t omega. That's it, right? So you get 20 log of t omega. Okay, so that's what you get in decibels. Now where do they intersect? They intersected omega equals 1 by capital T. So omega equals 1 by capital T remains the corner frequency. Okay, so no change in that, right? So this remains the same. Okay, now what is the slope of the high frequency asymptote? Slope of the high frequency asymptote is going to be plus 20 decibels per decade, right? So that's also pretty standard, right? So you repeat the same calculation, you substitute in terms of what to say 10 times omega, you will get 20 plus 20 log to the base 10 t omega. So between omega and from omega to 10 times omega, you have an increase of 20 decibels, right? So that's why the slope is 20 decibels per decade, right? So then you know, like how would this magnitude plot look like in this case? So once again, if I plot the magnitude curve for this, in decibels, what would happen? Let's say if this is 0, this is 20, right? So let's say this is 1 by capital T, 10 by capital T and 0.1 by capital T. Let me just use the same colors as before. So that we are consistent, right? I used pink for low frequency, yellow for high frequency, and okay, let's use the same color. So let's say I use pink for the low frequency asymptote. So the legend remains the same, right, as before. So how do I draw the high frequency asymptote? Please note that this is just an illustration. Low frequency asymptote makes sense only at low frequencies, obviously, right. So how do I draw the high frequency asymptote? 1 by t 0 is 1 point, and 10 by t it's going to be 20 decibels, right. So the high frequency asymptote is going to be this, so which has a slope of plus 20 decibels per decade, okay, and the approximation is going to be this, okay, that color. And as homework, okay, calculate the errors, the error in magnitude as before, okay, but you will see that it's a very simple process, but I want you to do it, right. So you will see that now at the corner frequency you will have an error of plus 3 decibels, okay, and one octave above and below you will have a what to say error of 0.97 decibels, whatever was minus becomes plus, okay, and one decade above and below the error will be 0.04, okay, almost close to 0. So the actual curve will be something like this, okay. So now you see that the high frequency amplitude, so at high frequencies the amplitude is increasing at the rate of, the magnitude is increasing at the rate of 20 decibels per decade, right. So in fact, like, so the factor Ts plus 1 is in fact like amplifying high frequency signals, okay, it is not attenuating, right. So this is like a high pass filter, right. So the higher the frequency, the greater is the scaling, right, the amplification of the input signal, okay. So that is the characteristic of capital Ts plus 1, okay. So the color legend remains the same, okay, that is why I am not rewriting it here, but you understand, right. So immediately you see that this is going to be a reflection, that is what we discussed in the last class. So you see that the magnitude plot of Ts plus 1 is just a reflection about the horizontal line passing through the 0 decibel point, right. So you see that it is just a mirror image, right, you just flip it, you will get the Bode plot of the magnitude plot of Ts plus 1. What about the phase plot? Let me draw it in the next page, okay. So what happens to the phase plot? So once again it is going to be a reflection, right. So what is going to happen? So what would the phase tend to as omega tends to infinity? It will tend to plus 90, right. At omega equals 1 by capital T, it will be 45 now. Why? Because please note that the phase of g of j omega now is tan inverse of t omega, not minus, it is just tan inverse, right, plus. So essentially if this is my 0 degrees and this is my 90 degrees and this is 45, so what is going to happen is that at 1 by capital T and let us say 10 by capital T and 0.1 by capital T, 1 by capital T the value is 45, right. So what is going to happen to the phase plot is that it is going to start from 0 and then pass through 1 by capital T and 45 and then settle to 90 asymptotically, okay. So that is what will happen to the phase, okay, of this factor 1 by capital Ts plus 1. So you see that it is just the reflection once again about the what to say 0 degrees line, right, the horizontal line passing through 0 degree, okay. So this is the these are the Bode plots, you know, the magnitude and the phase plot of the first order factor. No, please remember why we are doing it, because if you recall where we stopped in the last class, you know, you give me any transfer function, what I am going to do, I am just going to write the transfer function as a product of these individual building blocks, right? Once I do that, what's going to happen? I plot the magnitude plot and the phase plot of the individual blocks, and then I just add them. That's it, right? So then I get the magnitude and phase plot of the transfer function which I am given, okay? And that's what we are going to do. So today we learnt about first order factors, right, of the form 1 by capital Ts plus 1 and Ts plus 1, right? Tomorrow's class, we are going to look at second order factors, okay? We will see how to plot the Bode plots of second order factors, and then we will do an example, okay? So that's our action plan. Fine, yeah.